Within Chapter 7, we look at periodic properties of the elements. So this is a really nice extension of what we were looking at in Chapter 6, where we have different electron configurations. Now we're connecting it to the properties that those elements have, those atoms have. We're going to be able to make predictions for different properties and also offer explanations. So I listed a typical problem that we would see at the bottom there. Typical question, where we're asked to come up with a answer, a prediction for which of these would be the smallest, and then also offer an explanation for why. So within this chapter, we're going to see a combination of properties that we're going to predict, and then also the supporting explanations. When we begin by looking at the periodic table, two people we want to associate with that: Mendeleev for the organization of the periodic table, and Moseley for his contribution involving atomic numbers. Here I show different portions of 7.1 in the e-text. The idea that initially Mendeleev is credited with organizing the different elements, grouping them based on their physical and chemical properties, and finding repeating patterns, and then that guided the way that he sorted them or arranged them in the periodic table. What was noteworthy within this is it led to the prediction of new elements. It wasn't simply having a big figure or a big table that compiled all of the elements. By organizing it in this manner, he left vacancies. He left vacancies, for example, where the element germanium was to be found. So this was a powerful way of organizing the information. It wasn't just describing what was there, it led to future predictions. When we look at the modern periodic table, what we find are elements that were discovered in different eras. It's interesting that, at least to me, that the majority of elements readily form compounds, and so they're not found in nature in their elemental form. Which ones are? Things like carbon, sulfur, copper, iron, silver, gold, mercury. So many of these are ones that were known in ancient times. They could find or easily obtain mercury or silver or iron. So notice how so many of these were metals that were found, and you could just find them as is in nature. They weren't bound up necessarily in compounds. Things that were very reactive, like your alkali or alkaline earth, it wasn't until chemistry advanced where those could then be isolated that those could then be discovered. So the ability to isolate and remove elements from the compounds that they're bound in, that's one factor that influenced when they were discovered. Here's a description of Mendeleev's table. So pause for a second. What information did Mendeleev use to group the elements? Electron configuration, boiling point, number of protons, or all of these? What do you think? Well, boiling point is a physical property, so it makes sense that he might be organizing them with that being one of his concerns. Electron configuration, number of protons, those were both discovered well after 1860, so they can't be things that he was using when he was constructing the periodic table. Now, if we think back from chapter 6, though, the periodic table was a great tool to think about the electron configuration. So we need to turn that around. And by turning that around, what comes first was the organizational scheme on the periodic table. The fact that that then is consistent with the electron configuration tells us that the electron configuration must be something that is influencing the properties. The table is based on the properties. If that's also consistent with the electron configuration, then the electron configuration must somehow be telling us about patterns of the properties. That's what we're going to explore in this chapter. I mentioned the other scientist we want to associate with the periodic table is Moseley. So Moseley began working with Ernest Rutherford. His experiment was he was exploring what happened when different metals were bombarded with high-speed electrons, and he found that they emitted X-rays. They emitted X-rays that had different energies, their own unique frequency. This leads to the idea that the reason they're different is that different elements have different number of protons, and that the atomic number corresponds to the number of protons. On the periodic table, that's how we've been analyzing it. Hydrogen number 1, 1 proton, atomic number 1. Helium number 2, 2 protons. Lithium number 3. So the idea that the number of protons corresponds to the atomic number, and that was different for every element, that's an idea from Moseley. If you want to see what this experiment looks like, there's this video on YouTube that I think does a really good job showing the setup. So if you just Google Henry Moseley X-ray spectrometer, it's a 5-minute video. I think does a good job of explaining what's going on. There's this question within the e-text. As the energy of an orbit becomes more negative, does the electron experience a stronger or weaker attraction to the nucleus? Tell me about the radius. I'm going back to this because we want to again revisit the idea of potential energy. If I'm thinking about a more negative potential energy, I'm thinking of a stronger and stronger attraction. I'm thinking the orbit size decreases. What's causing this? More protons. So if Moseley is telling us something about atomic numbers, he's telling us something about the protons. Now, I mentioned that he was measuring emitted X-rays. How does an atom produce X-rays? Why would it depend on the number of protons? What's happening to the electronic energy levels as the number of protons changes? I'm sure you've been to the dentist and had an X-ray done. How do they make X-rays? Do they have a big box of X-rays? Where do the X-rays come from? And how could an atom emit X-rays? So we've been looking at the energy levels for hydrogen. And if we consider the spectrum, we would see that a hydrogen atom can emit in the UV, visible, or infrared. Atoms with more protons, they can emit X-rays. How does that work? Well, we've seen that when we have transitions going from 2 to 1, 3 to 1, those involved UV. If it was finishing at n equals 2, those are in the visible light. What about if it finished with n equals 3? Those were then in the infrared. In no case do I see X-rays. As we added more protons and more electrons, what did we see? We saw a shifting of the different energy levels. I'm pointing out that that shifting also, let's look at the 1s. It's moving lower in potential energy compared to hydrogen. As I increase the number of protons, I see the energy levels moving lower in potential energy. I'm also seeing the gap between n equals 1 and n equals 2 increasing. So the way that the experiment works for Moseley, this gap right here eventually is wide enough that it corresponds to X-rays. It's not wide enough in hydrogen because I don't have enough protons to pull that n equals 1 energy level lower and lower in potential energy. Within Moseley's experiment, he's bombarding his metal atoms with high-speed electrons. It takes a core electron that's in the 1s, moves it to an excited state, and then when an electron comes from a higher energy level like n equals 2 back down to n equals 1, this gap is now large enough that it's an X-ray. So a couple thoughts here. You will not need to be able to explain Moseley's experiment. You will not need to explain how X-rays are produced. So why am I mentioning this? I think that this demonstrates how the electronic energy levels shift when you have more and more protons. Chapter 6 was all about, let's think about the electron configuration. In Chapter 7, we'll now consider the positive charge that's in the nucleus, because that's crucially affecting the energy of these electrons. In Chapter 7, we're thinking about the protons once again. So how do we think about the protons? The protons are found in the nucleus. They're contributing to the nuclear charge. Chapter 7.2, really important idea. Something called the effective nuclear charge. Many properties are going to depend on the electron configuration and how strongly the outer electrons are attracted to the nucleus. Why are they attracted? Because we have more and more protons in the nucleus. We have opposite charges. That's what the different Q values are. That leads to the lowering in the potential energy. Our description for that is given here. Z is the number of protons in the nucleus. The attraction between the electron and the nucleus in a hydrogen atom, I think it's easy to understand. We just have one proton, one electron. But it becomes more complicated as we have more electrons. Why? Because we're going to have attractions between protons and the electrons, between the electrons with the electrons, which are repulsions, and we're interested in that combined attraction and repulsion. There's attractions between the protons and the electrons, but because there's repulsion between the electrons with each other, we find that the overall net attraction is less than that it would experience if we didn't have those electron-electron repulsions. How much less? That's what this expression here for the effective nuclear charge is telling us. The charge an electron experiences is due to the number of protons, Z, minus how it is shielded by the other electrons. When I look within this one, we want to consider what is the charge in the nucleus and then how is it being blocked by the other electrons. The textbook includes this analogy. It points out that the brightness of the light, that's like the charge in the nucleus. It's being diminished somewhat, though, by this frosted glass that is around it. Those are how other electrons are diminishing the charge. So if you are an outer electron and you want to see how bright the light is, well, it depends on the brightness of the light and then how it is being diminished by other electrons. That's what the effective nuclear charge is telling us. The brightness of the light is the number of protons, and it's being diminished by these shielding electrons. Now, it's going to be easy to determine the brightness of the light, the positive charge, because that's Z. That's the number of protons that we have. There's different ways to account for the shielding, though, and we're going to use a very simple model. We're going to count the core electrons, those that have a smaller n value, as shielding electrons. And I'll show you how that works. These electrons shield each other because electrons with other electrons, that's giving rise to repulsions. And we can calculate this effective nuclear charge for any electron. We will calculate it. It could be for the outermost electron. It could be for an inner electron. We can calculate the effective nuclear charge for any electron. So let's begin by looking at sodium. So if I look at sodium right here, it's number 11. 1s2, 2s2, 2p6, 3s1. I've just rattled off there what the electron configuration is. If I'm looking at that visually in terms of the potential energy, the 1s2 would be lowest, then the 2s2, then the 2p6, and then the 3s1 beyond that. We've looked, what does it mean to place electrons as a function of distance when we are looking at different radial probability distribution functions. So for the sodium, the 1s2 would be filled up, the 2s2, the 2p6, and then the 3s1 would be beyond that. Here's a picture that's trying to show the same thing. We have 11 protons in the nucleus. We have shielding electrons, which would correspond to the 1s2, the 2s2, and the 2p6. The charge that that outermost electron then experiences in the 3s, the way I would do the math for it, I would say that there are a total of 11 protons. There are 10 shielding electrons because that is the number of electrons that have a smaller principal quantum number. If I'm thinking about the 3s electron, I've got a total of 10 electrons that are lower in energy than that. 11 minus 10, positive 1 for its effective nuclear charge. If we think about how this could then show up on the periodic table, if we're thinking about the valence electrons for what their effective nuclear charge is, how do we do the math for that? Well, if I look at lithium, we can do the math easily for any of them. If I look at that valence electron for lithium, I see that there are 3 protons and that there are 2 inner electrons that are shielding it. So for lithium, 3 minus 2, positive 1, the effective nuclear charge for lithium. See if you can complete the values for boron, oxygen, and neon. Share ideas. Can you calculate the effective nuclear charge as you move across to boron, oxygen, and neon? And then I'll share my work. Here was my math for lithium. 3 protons, 2 shielding electrons, +1 for the effective nuclear charge. Here were the values for boron, oxygen, and neon as I moved across. For these valence electrons, the effective nuclear charge is increasing as I move left to right. It's reaching a maximum when I reach a noble gas. And then it starts over again. At neon, it had a value of +8. Remember, for sodium, it went back to being +1. It reset. Here's a figure showing the effective nuclear charge as you change the atomic number. First thing to point out within here, look at the effective nuclear charge for those inner electrons. The core electron, the 1s electron, if it was in lithium, beryllium, boron, carbon, nitrogen, etc. Notice how the effective nuclear charge just keeps going up, 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 up. There's nothing shielding it. You're just adding more and more protons, and the effective nuclear charge just keeps increasing. That's not what my periodic table looks like. That's not periodic at all. If this was an important factor for the properties, your periodic table would just be a line that just keeps going. But that's not what the periodic table does. It resets and starts over again. The periodic table is really a reflection of how the effective nuclear charge resets. It increases, as we just saw, as we move towards a noble gas. Then when we get back to an alkali, it starts over again, and then it increases up once again from there. The periodic table sure seems to be dependent on the effective nuclear charge for the valence electrons. That is the single most essential idea that I have in Chapter 7, and that's going to be used to explain various periodic properties. Coming back once again, the number of protons is easy to figure out. I just look at the periodic table for that. The shielding of the electron, there's a few different ways we can think about that, and that's why it shows a few different ways that you could calculate the values. One feature that I want us to be aware of when it comes to the shielding is it always the same for a particular column or is something else going on as we go down a column. Turns out for valence electrons going down a column, the effective nuclear charge is slightly larger than you would have thought because the core electrons are not as effective shielding as those clouds get bigger and bigger. So that would tell me that the effective nuclear charge for neon we just calculated as +8. For argon might be just a little bigger, 8.05, who knows, just slightly bigger. Our main trend that we want to be aware of is left to right. This is just trying to make you aware of an additional feature that changes that value just a little bit. We can consider effective nuclear charge not just for neutral atoms, we could think about it for ions too. In this simple shell picture, what does hydrogen look like? There's 1 proton and 1 electron outside of it. What would that same shell picture look like if I was looking at helium that was +1, lithium that was +2? Notice how the radial probability distribution functions get closer and closer to the nucleus. I think that's because they have different effective nuclear charges. Take a second. What would be the effective nuclear charge for hydrogen, helium+, and lithium 2+? In all of these cases, I don't have any shielding electrons. So for hydrogen, it would be +1, lithium +2. This would be hydrogen +1. For helium +1 cation, it would have an effective nuclear charge of +2. For the lithium 2+, it would have effective nuclear charge of +3. There's no shielding electrons in any case. So you notice that that inner electron is being pulled closer and closer to the nucleus. The size is being affected by the effective nuclear charge. We've spent some time in this video looking at the periodic table and this crucial idea of effective nuclear charge. I've just begun to point out how it's going to be used to predict different properties. So we really need a strong understanding of effective nuclear charge, and then we can use it to predict different properties. Two questions that I want to draw your attention to, end of chapter. The first one is back to this analogy. See if you can explain this analogy, 7.1. If you can, I think you have a really good sense of what's going on the periodic table. And the second one here is an application of the idea. Give that a try and we'll pick up from there in class.